Welcome to today's deep dive. I'm your host, and today we are getting into something that affects literally anyone who uses AI.
And I'm your resident expert for the day. And yeah, we've got some truly wild mathematical gymnastics to talk about.
We really do. So think about this for a second. Have you ever tried to feed a massive, 100-page PDF into an AI, fully expecting your computer's fan to just sound like a jet engine taking off?
Oh, absolutely. Or, I mean, if you're a developer, you're probably assuming the server bill for that one prompt is going to bankrupt your entire startup.
Right, because the sheer scale of what we are asking these models to process, it's completely unprecedented in the history of computing.
It really is. Honestly, it's genuinely a miracle that it works at all.
Yeah, usually when we think about computer memory, we picture this like pristine, rigid warehouse. Every pixel on your screen, every single letter in a Word document, it all has a designated, perfectly labeled box on a hard drive.
Exactly. It's all absolute bookkeeping, just a 0 or a 1.
Right, and it's a comforting way to think about data. We want our information perfectly preserved, exactly as we left it, with a clean index telling us where to find it.
But then you step into the world of massive artificial intelligence, and suddenly that pristine warehouse is just overflowing. We are looking at a memory landscape that is, frankly, on the verge of collapsing under its own weight.
Which is why today's deep dive is so fascinating.
Yeah.
We're basing this on 3 cutting-edge research papers, QJL, PolarQuant, and TurboQuant, that are entirely rewriting the laws of data compression. We're going to unpack the invisible, almost magical tricks that let AI read entire books without instantly running out of memory.
And to really understand the solutions in these papers, we first have to isolate the bottleneck. So modern AI, specifically transformer models, they rely heavily on this mechanism called a KV cache.
The key value cache.
Right, the key value cache. Think of it as the AI's short-term working memory. When an AI generates a long response, it absolutely cannot afford to reread your entire initial prompt from scratch for every single new word it spits out.
Because that would scale quadratically and take, forever.
Exactly, forever. So it saves a mathematical representation of what it has already read, and it keeps it on standby. It takes every token, every chunk of a word, and encodes it into these incredibly complex, high-dimensional vectors.
Those are the keys and values.
Yep, and they get stored in the cache. But here's the fatal flaw. As your conversation gets longer, or, as you upload bigger documents, this cache balloons exponentially. It just starts hoarding all of the extremely fast, extremely expensive GPU memory.
And then the whole generation process slows to an agonizing crawl.
Precisely.
Okay, let's unpack the traditional fix for this. Normally, if a memory cache is bloated, developers use a technique called quantization.
Right.
Which essentially just means compressing those highly precise, massive numbers into smaller, rougher numbers. I always think of it like saving a massive uncompressed raw photograph as a smaller JPEG file. You lose a little detail, but you save a ton of space.
That is the standard industry approach, yeah. But traditional quantization comes with this massive, unavoidable penalty: metadata.
The metadata.
Right, because to compress those numbers without completely scrambling what they mean, the system is forced to group the data into blocks. And then they have to store reference points, specific 0 points and scales, in full precision for every single block of data.
Just so the AI knows how to decompress it later.
Yeah, exactly.
So it's kind of like perfectly packing a suitcase to save space, but the airline forces you to attach a separate, bulky, hard plastic luggage tag to every single pair of socks in the bag.
That is a phenomenal way to visualize it.
Right, because suddenly the tags themselves are taking up as much room as the clothes.
Yeah.
You've defeated the whole purpose of packing tightly.
You really have, because depending on the size of the blocks, those mathematical normalization constant add like 1 or 2 extra bits of memory overhead for every single number. When you're dealing with billions of numbers, that metadata completely eats your compression gains.
Which means we need to figure out how to lose the luggage tags. And that brings us to the first of our 3 sources, introducing a method called QJL.
Yes.
The researchers here asked a fairly radical question. What if we just squash the data down so aggressively that the metadata doesn't even matter? Like, what if we compress the numbers down to a single bit?
It is a breathtakingly bold proposition. I mean, they're proposing taking these complex continuous floating point numbers and compressing them into literally just a 1 or a -1.
A single sign bit.
A single sign bit, nothing else.
Wait, I have to push back here. If you shrink a highly nuanced, high-precision mathematical vector into just a 1 or a -1, Doesn't the AI essentially get amnesia? I just
Well,
don't see how the model can possibly remain accurate if it's operating on that little information. The nuance is entirely gone.
you would assume the nuance is gone, right? But what's fascinating here is how they leverage a concept from numerical linear algebra called the Johnson-Lindenstrauss transform, or JL transform for short. Imagine taking a complex, highly detailed three-dimensional object, like a sculpted statue, and casting a harsh light on it to look at its two-dimensional shadow on the wall.
You absolutely lose the rich 3D volume.
Right, the shadow is just a flat, dark shape. But, and this is the key, the shadow preserves the fundamental relationships of the object. If the statue's arm is raised higher than its head, the shadow still reflects that spatial relationship perfectly.
Oh, I see where this is going.
Yeah, in the context of AI, the absolute raw values of the numbers matter significantly less than how those numbers relate to each other. When an AI is searching its memory, it calculates something called the inner product, which is a measurement of the relationship between the current word it's processing the query and the previous words sitting in its memory, the keys.
So QJL focuses purely on preserving that inner product relationship rather than hoarding the number themselves.
Yes, and they do it using this brilliant asymmetric trick. They apply this extreme one-bit shadow compression strictly to the key sitting in the cache. But when a brand new query comes in from the user, they apply the JL transform to it, but they leave the actual numbers unquantized.
You do not squash the query.
Exactly. The mathematical proof in their research demonstrates that when you calculate the inner product between this full precision query and the one-bit squashed key, the result is a perfectly unbiased estimate of their original high-precision relationship.
That feels like a magic trick. By only squashing half the equation, the math still perfectly balances out on average. You get massive memory savings because the stored cache is tiny, but the AI still accurately understands the relationships.
The math is airtight. However, there is one technical hurdle they had to solve before this could work in reality, and it has to do with outliers.
Right, because not all data is created equal. Some numbers in a neural network are vastly more important than others.
Exactly. The researchers mapped out the magnitudes of these key vectors across the different layers of the AI model. In the shallow early layers, the numbers are pretty uniform. But as you get into the deeper, more complex reasoning layers, specific coordinates develop massive, persistent spikes.
Those are the outliers.
Yeah.
And if you squash a massive, towering outlier into just a 1 or a -1 alongside a tiny, insignificant blip that also becomes a 1 or a -1, you lose the defining feature of that spike.
Right. The shadow no longer represents the statue.
So how'd they fix it?
QJL elegantly segregates them. It identifies these huge spikes during the initial reading phase, and it treats them entirely independently. It applies two separate copies of the quantizer, one for the normal sea of data, and one specifically tailored to protect the outliers.
That's incredibly smart. And the results in the paper are striking. I mean, they demonstrate a 5x memory reduction using just 3 bits per floating point number on average, with literally 0 drop in accuracy on complex tasks from the long bench benchmark.
QJL fundamentally proves that extreme compression is possible if you focus entirely on preserving the relationship between the data points.
Okay, so squashing everything to a 1-bit shadow works brilliantly if you just need rough relationships. But what if a specific AI task requires absolute high fidelity? Say we want to use 2 bits or 4 bits for a clearer picture, but we still can't afford that metadata luggage.
Well, then we've essentially hit a wall with traditional math.
Right, which means we have to stop using traditional math. We have to change the coordinate system entirely. And that brings us to the philosophical shift in our second paper, PolarQuant.
Yes.
This paper argues that the root cause of all our metadata overhead isn't the compression algorithms themselves. The problem is the Cartesian coordinate system we are forcing the data into. Here's where it gets really interesting. Let's visualize this. Think about how we normally map things out in everyday life. We use a Cartesian grid. If I'm giving you directions to a coffee shop, Cartesian coordinates would be like walk 3 blocks north and then 4 blocks east. You need 2 pieces of distinct, independent information to find your spot.
And in the high-dimensional space where AI operates, you don't just have an X and a Y, you have thousands of those specific independent coordinates.
Right.
Tracking the individual scale and variance of all those different directions is exactly why traditional quantization required those clunky metadata tags. You had to keep a record of how big every single axis was.
But PolarQuant throws out the Cartesian grid entirely and uses a compass instead. Polar coordinates. So instead of telling you 3 blocks north, 4 blocks east, I just give you an angle and a straight line distance. Point your compass exactly 53 degrees and walk 5 blocks.
It is an incredibly elegant geometric shift. By transforming the AI's complex embeddings into polar coordinates, meaning angles and radii, the data behaves completely differently. But to make this actually function for data compression, PolarQuant introduces a crucial, kind of counterintuitive first step.
Which
is random preconditioning.
Meaning they shuffle the deck before they deal the cards.
In a geometric sense, yeah. They apply a random mathematical rotation to the entire massive data set before doing any compression at all. They essentially spin the high-dimensional space. And when you randomly rotate thousands of dimensions of data, the magic of statistics kicks in.
Wait, why does randomly spinning data help us compress it? That just sounds like you were creating chaos.
It sounds chaotic, I know, but it relies on a foundational concept called the central limit theorem. Without getting bogged down in academic formulas, the theorem basically states that when you mix a massive amount of independent random variables together, their sums always average out to a normal distribution.
A bell curve.
A bell curve. By randomly rotating the high-dimensional data, we are essentially mixing all those thousands of coordinates up. The chaos, mathematically, inevitably, settles into a perfect, predictable bell curve.
So you're essentially using the laws of statistics as a loophole to bypass the need for bookkeeping.
Yeah.
You force the data into a shape you already know.
Yes. Because once you force the data into that perfect bell curve, something incredible happens when you convert it to polar angles. Those angles do not spread out evenly in a circle. They predictably, mathematically concentrate around a very specific angle.
Wait, really? What angle?
Pi over 4, or 45 degrees if you prefer.
Every single time. Just by spinning the data first.
Every single time. The paper derives the exact analytical probability distribution for this clumping effect. And if we connect this to the bigger picture, this is the absolute genius of PolarQuant. Because we know exactly what this clump distribution looks like mathematically before we even look at the specific data inside the AI.
We don't need to store any metadata to normalize it.
Exactly. We don't need the luggage tags because the laws of physics guarantee that all the luggage is inherently the exact same shape.
Oh, wow. That feels like a massive cheat code. But practically speaking, how do they actually map thousands of dimensions into angles? It can't just be one flat 2D circle with thousands of points on it.
No, it requires a recursive Polu transformation. Imagine a massive tournament bracket for geometry. You take the thousands of raw coordinates and you pair them up. Coordinate 1 and 2 become a single radius and a single 2D angle. You do that for all of them.
Okay, I'm following.
Now, you take all the resulting radii, pair those up, and find the angles between them. You do this recursively, building logarithmic levels of angles until you reach the top of the bracket.
Okay, I see the bracket, but how does that save memory?
Because of how the recursive math works out, that very first level of angles at the bottom of the bracket covers a full, wide, 360-degree circle from 0 to 2 pi. To capture that wide variance accurately, the algorithm allocates 4 bits of memory.
Makes sense.
But for every subsequent level moving up the bracket, the math restricts the angles tightly between 0 and 90 degrees. They are squeezed into a single quadrant. Because they are so tightly packed, the system only needs 2 bits to capture them perfectly.
They are rationing the bits based on how wide the angles are mathematically allowed to spread. The efficiency there is just stunning. And the result, the paper details a 4.2x compression rate. And crucially, it absolutely dominated on the needle in a haystack test.
Yeah, that test is the ultimate proving ground for these systems.
Just for those who might not know, the needle in a haystack test is where researchers hide a single, highly specific, random sentence deep inside a massive book-length prompt and force the AI to retrieve it.
Right.
Older methods like token eviction, where the AI just deletes parts of the conversation it thinks are unimportant to save memory, they often fail this test catastrophically because they accidentally delete the needle. But PolarQuant aced it.
It proves that changing the map itself, shifting from Cartesian grids to polar compasses, can unlock efficiencies that traditional numerical compression just cannot see.
Okay, so we've changed the map, but there's still a fundamental physical tension we haven't resolved. And that brings us to the final summit of our deep dive. The third paper, TurboQuant.
Yes, TurboQuant.
TurboQuant steps back and identifies a structural flaw in absolutely all compression algorithms, whether they use one-bit shadows or polar angles.
It highlights a deep mathematical conflict between two different ways of measuring accuracy. On one hand, you want to minimize the overall error of the data's macro shape. This is called mean squared error, or
Yeah.
MSE.
Okay.
On the other hand, as we discussed with QJL earlier, the AI desperately needs to preserve the specific micro-relationship between data points of the interproduct.
So what does this all mean, going back to our suitcase metaphor? If I perfectly pack my suitcase to minimize wasted space, which is optimizing for MSE, why does that ruin my ability to quickly find a specific shirt? Why are these two things at odds?
Because to optimize for pure space, you might pack the suitcase so incredibly tight to fit into the airplane's overhead bin that you physically detach the sleeves of your dress shirt and stuff them inside your shoes.
Oh, I see.
The overall space is perfectly optimized. There is zero wasted room. But when you arrive at your hotel and go to unpack to find that specific shirt, the inner product, you pull out a torso without sleeves.
Right, the relationship between the pieces is broken.
Exactly. The overall package was incredibly tight, but the specific distances and angles between your items are ruined.
Hmm.
An MSC optimal quantizer makes structural compromises to make the whole package small. When you do that, especially at very low bit widths, you inherently introduce a systemic bias into the specific angles between individual data points.
So if you optimize for the macro, you break the micro. And if you optimize for the macro falls apart. How do you get a perfect, unbiased quantizer that minimizes both simultaneously?
TurboQuant solves this with what I can only describe as a two-stage masterpiece. Stage 1 tackles the macro, the mean squared error. Similar to PolarQuant, it starts by randomly rotating the data. This creates a highly predictable statistical distribution, specifically a beta distribution on each coordinate.
Another predictable curve born from chaos.
Exactly the same principle.
Okay.
Because this beta distribution is perfectly mathematically predictable, the researchers can apply an optimal scalar quantizer, specifically the Lloyd-Max algorithm.
The Lloyd-Max algorithm. For those who haven't spent their weekend reading dense information theory textbooks, it is essentially the mathematical gold standard for finding the absolute perfect, statistically optimal places to chop a continuous curve into discrete chunks.
It is the ultimate tool for minimizing overall shape error. It perfectly packs the suitcase. But as we established, this MSC optimization introduces that nasty bias to the inner product. It detaches the shirt sleeves.
Right.
So the TurboQuant algorithm immediately moves to stage 2. They look at the leftover error from stage 1, the tiny mathematical crumbs that were lost during the Lloyd-Max compression. This is called the residual.
The detached sleeves.
Yes.
Right.
And they take that residual error and they hit it with the QJL 1-bit trick from our very first paper.
Hold on, I need to push back on this. You're saying they run a highly complex MSE compression and they just slap a 1-bit shadow trick on the leftovers. Doesn't compounding the compression just compound the errors? You are squashing data that has already been squashed.
You would think so, but remember, the unique property of the QJL 1-bit trick, it is mathematically unbiased when calculating the inner product. By applying it strictly to the leftover residual error of the MSE quantizer, it doesn't compound the error. It acts as a perfect mathematical counterbalance.
Oh, wow. So stage 1 packs the suitcase perfectly, detaching the sleeves to save space. Stage 2 leaves a tiny, mathematically perfect 1-bit map inside the shoe, telling the AI exactly how the sleeves reattach to the torso. It perfectly corrects the inner product bias without taking up any real space.
The performance of this two-stage approach is staggering. To truly understand just how staggering, we have to talk about Claude Shannon.
The undisputed father of information theory.
Shannon proved mathematically, decades ago, that there is a hard physical limit to how much data can be compressed before the information is irreversibly destroyed. It's called the Shannon lower bound. You literally cannot compress data beyond this point, no matter what algorithm you use.
Yeah, and TurboQuant.
TurboQuant pushes right up against this absolute physical limit. The paper shows it operates within a tiny constant factor, about 2.7 of the Shannon lower bound.
It's literally bumping its head against the ceiling of physics. And practically speaking, the paper shows it achieves absolute quality neutrality for AI at just 3.5 bits per channel. The AI literally cannot tell its memory has been compressed. And this isn't just a trick for large language models generating text, is it?
No, the broader applications are massive. TurboQuant completely crushes traditional product quantization methods in nearest neighbor search. That is a foundational technology powering vector databases and RAID systems retrieval augmented generation.
So when a company builds an AI customer service bot, that has to instantly search through 10,000 dense company manuals to find a specific policy.
TurboQuant allows that system to achieve higher recall accuracy with essentially zero indexing time because it doesn't need to painstakingly learn the data structure beforehand. It just relies on the inherent statistical laws of the universe we discussed.
Incredible. We have covered a tremendous amount of ground today. We started by looking at how QJL squashes data into a one-bit shadow to preserve vital relationships without needing metadata tags.
Right.
Then we explored how PolarQuant completely changes the geometric map using polar compass angles and random rotation to force data into natural, highly compressible curves. And finally, we saw how TurboQuant stacks these philosophies, balancing perfect overall shape with unbiased relationships to practically touch the absolute mathematical limits of data compression.
The rapid evolution of these techniques, jumping from traditional metadata to hitting the Shannon limit in such a short window of time, is truly remarkable.
It really is. The next time you upload a massive document to an AI, or you query a giant vector database, take a second to appreciate the invisible mathematical gymnastics happening behind the glass. There are algorithms spinning high-dimensional geometry, casting one-bit shadows, and mathematically reattaching shirt sleeves, all so you don't have to wait an extra 3 seconds for an answer.
Which leaves us with a profound final thought to mull over. If algorithms like TurboQuant are already hitting the Shannon lower bound, the absolute mathematical bedrock of compression, where does the next great leap in AI efficiency possibly come from?
That's a great question.
Right. If we mathematically cannot compress these numerical representations any further, will we eventually have to completely abandon the transformer architecture itself? Or is there an entirely new dimension of data, an entirely new map that we haven't even thought to compress yet?
It genuinely makes you wonder, if we can't pack the suitcase any tighter, maybe we have to invent a completely different kind of travel. We will leave you to think about that one.